The third method is the integration method or the integral method. Okay, so I have listed some important features of the integration method. First of all, this method is a trial and error method. And remember, a trial and error method is always a laborious method or a time consuming method. Okay, and sometimes it may finish off very early, but in some cases it may be lengthier method. Okay, second, this integration method is only applicable for those reactions where the order is an integer. So this method is not applicable for a reaction having a fractional order. So these two are the limitations or disadvantage of this method. The advantage or the plus point of this method is you can determine the rate constant of the reaction simultaneously with the order, and the rate constant is almost accurate. Okay, so we can determine the rate constant accurately. Okay, then one more feature of this method, which is actually a disadvantage of this method, is sometimes it may lead to an ambiguous, okay, result. Okay, it may put some doubt into our mind. For example, if the order of a reaction is 1.85 or 1.9, which is almost equal to the integer 2, so strictly speaking, a differential method would have given order as 1.8. But since this 1.8 or 1.9 is almost equal to 2, the integral method ಅಲ್ಲಿ ಏನಾಗಬಹುದು ಅಂದ್ರೆ ಈ 1.8 ಗೆ ನಮಗೆ ಏನು ಡೇಟಾ ಸಿಕ್ಕಿರುತ್ತೆ, that data may fit into the graph of a second order reaction, and this method may suggest us that it is a second order reaction. Okay, suppose if the order of a reaction is 1.1, okay, or 1.15, which is a fractional order, but this method, okay, may suggest that the order of the reaction is 1. Yakandre sometimes what may happen that if the order, which is actually a fraction but very close to the integer, anta ಕೇಸಲ್ಲಿ ಏನಾಗುತ್ತೆ ಅಂದರೆ ambiguous result ಬರ್ಬೋದು, confusion ಬರ್ಬೋದು. That is one disadvantage of this method. And this method, okay, can be used to determine the order of the reaction either numerically or graphically. You can either use the graphical approach or the numerical approach. So what is this method? Let us try to understand. So first what we have to do is we have to collect some experimental data. So carry out a reaction and at different intervals of time experimentally determine the concentrations of reactant and concentration of product formed. So we have to find out the values of X, that is the concentration of the product formed, and A minus X, that is the concentration of the reactant remained unreacted at different intervals of time t. So we have three data: time, X, and A minus X. So now what we do is we will try to fit these data, that is X, A minus X, and T, into integrated form of rate equations. So starting from zeroth order reaction, first we will try with zeroth order reaction. If everything works well and if the reaction is zeroth order, okay, we will get the answer in the first stage itself. Then we need not try first order, second order reaction. Otherwise, if the zeroth order reaction does not work, if it fails, then we have to go for first order reaction. If it does not work, then we have to go for second order reaction. That is by trial and error method approach. Okay, we have to test these equations, the integrated rate equations, one after the other. Okay, so starting with zeroth order. Alternatively, what we can do is either we can follow a graphical approach by plotting the characteristic graph of a zeroth order, first order, and second order reaction. Okay, remember in our earlier classes we discussed about the characteristic graphs of zeroth order, first order, second order reactions. Now that those basic topics that were discussed earlier, okay, now they are handful here, they are handy here. Okay, so either we can try to fit this data into equation, which is a numerical method, or we can try to fit this data into a graph, which is a graphical method. What I am saying, I will take an example and try to explain you. So first step is we have a data. We have, for a particular chemical reaction, we have data, that is we have X, A minus X, and time t. Okay, now let us start with the zeroth order reaction. Let us start with the zeroth order reaction. What is the expression, integrated form of rate equation for zeroth order reaction? K is equal to x by t, or you can also write it as x is equal to k into t, or you can also write it as a minus x is equal to minus a into t plus a. For all these equations, you please refer to the earlier videos. Okay, in the first 3 video lectures I described all these equations. Okay, so these are the integrated form of rate equations for a zeroth order reaction. Now what I will do is, I have experimental data, okay, at different time intervals t1, t2, t3, t4, t5. I have x1, x2, x3, x4, x5. That is the concentration of product at different time intervals. Also I have this data, a minus x at 1, a minus x value at time interval 2, a minus x at time interval 3, a minus x at time interval 4, a minus x at time interval 5, so on. So I have this data. Now first what I will do is, I will try to calculate x by t from each of these data. Okay, so I will try to calculate x1 by t1. Similarly, I will try to calculate x2 by t2. I will try to calculate x3 by t3, x4 by t4, and x5 by t5. And if all these values appear to have same value, okay, if all these values are one and the same, what does it suggest? It suggests that x by t should be a constant. Okay, and in fact it will be a constant for a zeroth order reaction. Yakandre for a zero order reaction, what is x by t? X by t is nothing but equal to k, which is a constant. So if all this x1 by t1, x2 by t2 up to x5 by t5 ಇದೆಲ್ಲನೂ ಸೇಮ್ ವ್ಯಾಲ್ಯೂ ಬಂದಿದೆ ಅಂದರೆ, ಕಾನ್ಸ್ಟೆಂಟ್ ವ್ಯಾಲ್ಯೂ ಬಂದಿದೆ ಅಂದರೆ, ಇಟ್ ಮೀನ್ಸ್ ದಟ್ ರಿಯಾಕ್ಷನ್ ಇಸ್ ಎ zeroth order reaction. ಮತ್ತು ಆ ಕಾನ್ಸ್ಟೆಂಟ್ ವ್ಯಾಲ್ಯೂಸ್ ಏನು ಬರುತ್ತೆ, ಓಕೆ, ಇಫ್ ಕಾನ್ಸ್ಟೆಂಟ್ ವ್ಯಾಲ್ಯೂಸ್ ಏನು ಬರುತ್ತೆ, okay, constant values in barutte, that is nothing but the rate constant of the reaction. So from a single data we have determined both the order of the reaction as well as the rate constant of the reaction. So ಇದು constant ಬಂದಿದೆ ಅಂದ ಕೂಡಲೇ what you can say, it is a zeroth order reaction. And also we can get the values of the rate constant. So this is the numerical method. Alternatively, what I can do is, I can try to plot the characteristic graph of a zeroth order reaction. I already have this data, so I will try to plot a graph. What is the characteristic graph for a zeroth order reaction? You have to plot a graph of x versus t, or you have to plot a graph of a minus x versus t. Okay, so by using this data, I will try to plot x versus t, and if I get a straight line passing through origin, it means that it is a zeroth order reaction. And from the slope you can find out the rate constant of the reaction. So again, simultaneously determination of order and rate constant is possible. Alternatively, a minus x versus t according to this equation should be a straight line with a negative slope and a definite intercept. Okay, the value of this intercept is the initial concentration A, and the slope gives the rate constant. So if you get this characteristic graph from this data, it means that it is a zeroth order reaction. Suppose if you do not get this characteristic graph, it immediately means that it is not a zeroth order reaction. Alternatively, in the numerical method, if you do not get constant values, suppose x1 by t1 is not equal to x2 by t2, it clearly shows that this is not a valid equation for this particular chemical reaction. So therefore the reaction is not a zeroth order reaction. So either by numerical method or by the graphical method, you can test whether the given reaction follows zeroth order kinetics. If the reaction does not follow the zeroth order kinetics, then we have to test the first order kinetic equation and graph. Okay, so what is the first order equation? Okay, again we have all this data. I will rub it off. So we have all those data. Now we have to test a first order reaction. First order reaction. Okay, what is the first order reaction? It is K is equal to 2.303 divided by t into log of a by a minus x, or it can be also written as log of a minus x is equal to minus k into t divided by 2.303 plus log a. Okay, or you can also write it as log of a by a minus x is equal to k divided by 2.303 into t. So again I have all those data. First what I will try to do is, say for example, if I am verifying by numerical approach, then what I will do is at time t1 I will calculate 2.303 divided by t1 into log of a by a minus x 1. Okay, I am substituting the data at t is equal to t1, the respective reactant concentration. Similarly, I will calculate 2.303 divided by t2 into log of a by a minus x at t2. ಅದೇ ರೀತಿ up to time interval t5, that is 2.303 divided by t5 into log of a divided by a minus x at t5. Okay, and if all these values are the same, if all these expressions gives the same value, a constant value, it clearly indicates that this equation is a valid equation for the chemical reaction. Therefore the reaction follows a first order kinetics, and the constant value we get here is nothing but the rate constant of the reaction. Alternatively, graphically, okay, with the data that are written here, okay, you can plot a graph of either log a by a minus x versus t, in which case you should get a straight line passing through origin, and from the slope you can find out k is equal to 2.303 into slope. Or alternatively, you can plot log of a minus x versus t. It will be a straight line with negative slope and definite intercept. The intercept gives log a, and from the slope, the magnitude only, okay, we get k is equal to 2.303 into slope. So if you get this characteristic graph, okay, a straight line passing through origin in the first case, or a straight line with negative slope and definite intercept for log a minus x versus t, it clearly indicates that it is a first order reaction. So in either approach you can find out both rate constant as well as the order of the reaction. If this does not work out, then we have to go for testing the second order reaction, then third order reaction, and so on. So that is why I told you this is a time consuming method, a laborious method, because if everything goes fine and the unknown reaction that was given to you followed a zeroth order reaction, then your testing will end in the first step. Suppose if you are given in the third order, if you are given a third order reaction, then you are unaware of the order of the reaction, so you cannot immediately test the third order reaction. You have to follow the same order. First you have to try the zeroth order, you will come to know that it is not valid, then you have to test the first order, then you have to test the second order, then you have to test for the third order reaction. Immediately you cannot test for the third order reaction. So this is a time consuming method. Okay, so this integration method has its own advantage as well as disadvantage, as I described at the beginning of this topic. So this is about integration method. The fourth method that we will now discuss is the method of half-life. The fourth method is the method of half-life. So as the name suggests, we have to measure the half-life of the reaction, and using the data of half-life we have to find out what is the order of the reaction. In my earlier lecture, okay, I described the importance of the relation between half-life and order of the half-life and the concentration of the reactant. So the relation between half-life and the reactant concentration in fact depends on the order of the reaction. As the order of the reaction changes, the relation between half-life and the reactant concentration also changes. For example, for a first order reaction, half-life is independent of the reactant concentration. For a zeroth order reaction, half-life is in fact directly proportional to the concentration of the reactant. Similarly, for a second order reaction, half-life is inversely proportional to the reactant concentration. So the relation between half-life and concentration of the reactant depends on the order. So this fact we are using here for determining the order. We are trying to find out the relation between half-life and concentration, and if we establish the relation between half-life and concentration, then immediately one can come to know what is the order of the reaction. In general, the half-life of an nth order reaction is given by T half is directly proportional to 1 divided by a to the power n minus 1. That is, T half is inversely proportional to a to the power n minus 1, where a stands for the initial concentration of the reactant and n stands for the order of the reaction. So there are two different approaches. I will discuss both of them. The first approach is a numerical approach, which is very easy. And as I already told you, a numerical approach does not require many data. It requires only two data. Whereas the second approach, which is more general and a graphical approach, it requires at least 4 or 5 data, and therefore it is quite reliable or quite accurate. So here what we are doing is we are carrying out the reaction. Okay, we carry the reaction at two different initial concentrations A1 and A2. We are carrying out the reaction, same reaction, at two different initial concentrations A1 and A2. So we are carrying out only two runs, and experimentally we determine the half-lives T1 and T2. Okay, I will simply call half-life as T1 and T2. You can also write it as T half 1 and T half 2. Okay, let us not make that much complicated. So I simply write half-life as T1 and T2. T1 is the half-life for the reaction with initial concentration A1, and T2 is the half-life of the reaction with initial concentration T2. So this T1 and T2 may be having same value or different values depending on the order of the reaction. So now let us use this equation 1 for the reaction carried out at concentration A1 and reaction carried out at concentration A2. So for reaction 1, half-life T1 can be written as inversely proportional to A1 to the power n minus 1. And similarly for the second reaction, you write T2, the half-life, is inversely proportional to A2 to the power n minus 1. Okay, so changing the concentration has no effect on the order of the reaction. Okay, so if I take the ratio 3 by 2, okay, you get T2 divided by T1. Okay, when I am taking the ratio of two similar equations, this proportionality constant cancels with each other, so you can replace the proportionality by equal sign. So it becomes T2 by T1 becomes 1 by A2 to the power n minus 1 divided by 1 by A1 to the power n minus 1. So that is T2 by T1 is equal to A1 by A2 to the power n minus 1. Okay, now let us take log on both the sides. You get log of T2 divided by T1 is equal to n minus 1 into log of A1 by A2. Okay, since we are interested in finding out the values of n minus 1, we can write n minus 1 is therefore, okay, log of T2 divided by T1 divided by log of A1 divided by A2, which gives n is equal to, therefore, if I shift minus 1, you get 1 plus log of T2 divided by T1 divided by log of A1 divided by A2. So you can find out the order of the reaction. You can find out the order of of the reaction by using this equation 4. Again, if whether the reaction is of fractional order or integral order, you can calculate the order by using this equation. So the only data you need to find out the order is the values of half-life T1 and T2. So this half-life, once determined experimentally, okay, you can find out the order of the reaction because the values of A1 and A2, the initial concentration of the reactants, are already known to you. So you can find out the order of the reaction. And as you can see, you require only two informations, two data, T1 and T2 at concentrations A1 and A2. So this method is less time consuming, but it is less accurate. It may become less accurate because we are handling only two data. The more general method or approach is where we at least find out half-life at 4 or 5 different concentration and then plot a graph from which we can find out the order. So the second approach is more accurate and reliable. So for that we should use a general expression for half-life of an nth order reaction. Okay. Okay, so the second method uses the general expression for half-life. For a general nth order reaction, T half is equal to 1 divided by n minus 1 into k into 2 to the power n minus 1 divided by a to the power n minus 1. So this is the general expression for T half. Okay, because all these n minus 1, k, 2 to the power n minus 1, minus 1, everything is constant. We wrote T half is inversely proportional to a to the power n minus 1 in the previous slide. Okay, so this is the general expression for half-life of the reaction. Now this can be written as T half is equal to, let me collect all the constant terms together. So I will write it as 2 to the power n minus 1 minus 1 divided by n minus 1 into k. All these are constants. So here you have 1 divided by a to the power n minus 1, or T half is equal to 2 to the power n minus 1 divided by n minus 1 into k. If I take this to numerator, this becomes into a to the power 1 minus n. Okay, so let me take logarithm on both these sides. You get, therefore, log of T half is equal to log of, okay, all these terms I will write within the flower bracket, 2 to the power n minus 1 divided by n minus 1 into k, plus, because you have a into b, so log of a into b is log a plus log b, so plus, here I have log of a to the power x, which is x into log a, so we can write as 1 minus n into log a. This is the logarithmic form of equation 1. Now if you carefully look at this equation, this term here, okay, n is a constant, order is a constant, k is a constant, so this whole term works out to be a constant, and this term 1 minus n is also a constant. So the only variable is T half and a, that is log T half and log a. If you vary the concentration, okay, log T half also varies. So this equation is of the form y is equal to c plus m into x. Okay, so what I will do here is vary the concentration of the reactant and find out the different half-lives. Okay, how to vary the concentration? I told you when I discussed the half-life. You can find out the half-life in two methods. One single run, take a single run and first find out first half-life, second half-life, third half-life, fourth half-life, fifth half-life at a different concentration of the reactant at a different time interval using a single run. Or alternatively, what you can do is you carry out 5 different runs with 5 different initial concentration and just find out the first half-life for each run. I repeat, one run, single run of the experiment at a different concentration of the reactant at a different time intervals. First find out first half-life, second half-life, third half-life, fourth half-life and fifth half-life. Okay. Alternatively, what you can do is carry out 5 different runs at 5 different concentrations and only find out the first half-life. You can find it out in any one of this method. Okay, so you have a data of concentration of the reactant and the half-life, corresponding half-life. Now what you can do is plot a graph of log T half versus log A, and according to this equation it should be a straight line. Okay, it should be a straight line with an intercept. The intercept is given by this term. Okay, and finding out the intercept, okay, you can find out the value of this log term, and the slope of this is nothing but 1 minus n, and you will get a positive slope if n is less than 1. That is 1 minus n is positive. If n is less than 1, then you get a positive slope. Alternatively, you will get the graph of log T half versus log A straight line with negative slope. Okay, so the slope is 1 minus n, but with a negative slope if n is greater than 1. If n is greater than 1, 1 minus n is negative, then the straight line will have a negative slope. So you will get a positive or negative slope depending on whether n is less than 1 or greater than 1. So from the slope you can establish what is the order of the reaction, and once you know the order of the reaction from the intercept and knowing the order from this term, you can find out what is the rate constant of the reaction. So compared to the earlier approach number 1, this method is more reliable because you are working now with more number of data, and the second advantage of this method is simultaneously, okay, you can find out the rate constant of the reaction by working out the value of this intercept. So this method is called as the method of half-life. The fifth method, okay, is a graphical method. It is a less known method, so I will not go into much details of this method. I will only explain, okay, the important points of this method. So the fifth method is okay, this is a less established method or less used method, so I will only briefly explain this method. Now we know that the rate of the reaction depends on the concentration of the reactants to the power n, where n is the order of the reaction. So in general you can write the rate of the reaction dx by dt is equal to k into a minus x to the power n. Suppose if the reaction is zeroth order, okay, zeroth order, you write d by dx is equal to k into a minus x to the power 0, that is k. Okay, if it is a first order, dx by dt is equal to k into a minus x to the power 1. If it is a second order, you write dx by dt is equal to k into a minus x square, and so on for third order, fourth order. So what we are doing is experimentally we measure the rate of the reaction at different intervals of time. So experimentally find out dx by dt at different time intervals, and also experimentally find out the values of a minus x at a different time interval, and then try to plot first dx by dt versus a minus x to the power 1. Okay, because if you look at this equation is of the form y is equal to mx, c is equal to 0, so y is equal to mx, where y is dx by dt, x is a minus x to the power 1, and m is nothing but the rate constant. So let us try to plot dx by dt versus a minus x to the power 1. So if the reaction follows a first order kinetics, it means that it follows this equation. In that case, the plot of rate dx by dt versus a minus x to the power 1 according to this graph should be a straight line passing through origin. So if this graph is obtained, then it means that the reaction is a first order reaction and the slope of this reaction of this graph is rate constant k. Suppose if this graph is not obtained, it means that the reaction is not a first order reaction. Then you have to try for the second order graph. Okay, already you have this data dx by dt. Now let us look at the second order equation. The second order equation is also of the form y is equal to mx plus c, but c is equal to 0. So what is y here? Dx by dt. Now x is a minus x square. So we have to now plot a graph of dx by dt minus a minus x square. Okay, and if the reaction follows a second order reaction, it should satisfy this equation. It means that the plot of dx by dt by versus a minus x square should give a similar result like y is equal to mx. So you should get a straight line passing through origin, and if you get this straight line, the slope of the straight line establishes the value of rate constant k. So if this graph is not obtained, then you have to try the graph of the third order reaction. That is, you have to plot a graph of dx by dt versus a minus x cube, and it should be a straight line passing through origin with the slope value is equal to k. And if you don't get a straight line, then you have to test the fourth order graph and so on. So this is also a trial and error method. Okay, a trial and error method, but we are using this graph, okay, of dx by dt versus a minus x to the power n, wherein is 0 1 2 3 etc. So this is a less used method, less frequently used method. So in most of the textbooks you will not come across this method frequently. If n is equal to 0, that is a zeroth order reaction, then we need not plot any graph because dx by dt will be equal to rate constant k. So you measure the rate at a different intervals of time, and we find that you are getting the constant value of rate. So this fifth method is called as graphical method. The last method, which is actually not a method, it is a technique that can be used for the above five methods, that is differential method, Van't-Hoff differential method, or integral method, or graphical method, or fractional order method. So sorry, half-life method. ಐದು ಮೆಥಡಿಗೆ ಈ ಆಸ್ಟ್ವಾಲ್ಡ್ ಟೆಕ್ನಿಕ್ ಅನ್ನು ಯೂಸ್ ಮಾಡಬಹುದು. That technique is called as Australs isolation technique or Australs isolation method. Let us understand what is Australs isolation method. So this Australs isolation method is applicable if there are more than one reactants involved in the reaction. Okay, if we go back to the 5 earlier methods that we discussed for determination of order, okay, if you carefully look into those discussions, in all the discussion we unknowingly imagine that there is only one reactant or one type of reactant involved in the reaction, but in most of the chemical reaction you have more than one type of reactants involved in the reaction. Okay, you can have a plus b plus c giving product, where there are 3 different types of reactants involved in the reaction. So the first 5 methods that we discussed will not be applicable if there are more than one type of reactants. So in such case we have to make some modifications to those method, and that modification was suggested by Ostwald, which is called as Ostwald's isolation method. Okay, so what is this isolation method? Let us try to understand. Suppose if I have a reaction A plus B plus C giving product, okay, and the rate equation for this reaction is K into concentration of A to the power A into concentration of B to the power B into concentration of C to the power C. So the order of the reaction with respect to reactant A is A, reactant B is B, reactant C is C. So the total order of the reaction N is A plus B plus C. So what we have to do is to find out the overall order of the reaction. First we have to find out the order of the reaction with respect to reactant A. Okay, then we have to find out the order of the reaction with respect to reactant B, and then we have to find out the order of the reaction with respect to C. Okay, first let us try to understand what is exactly order of a reaction. Order of a reaction tells us how the rate of the reaction depends on the concentration of the reactant. Okay, so if, say for example, a reaction is first order with respect to A and another reaction is second order with respect to A. What do you understand from this information? What we understand from this information is, for the first case where the order was equal to 1, the rate decreases with respect to the concentration of A gradually. Whereas in the second case where the order of the reaction was 2, the rate decreased as the second power of A. So the rate decreases much faster with respect to concentration of A. So the reactant A and its concentration has more effect on the rate in the second order case compared to first order. Suppose if I have a reaction where the reaction is third order with respect to A, then it is the third order reaction where the reactant concentration has greater effect on the rate. So greater the effect of the concentration of a reactant on the rate, greater will be the order. So if when I say I am determining the order of the reaction with respect to a reactant A, it means I am finding out how the rate of the reaction varies with respect to the concentration of the reactant. So first let us try to find out the order of the reaction with respect to reactant A. That is, I am trying to find out how the rate changes as the concentration of the reactant A changes. But there is a problem now. Why? Because when the reaction occurs, not only the concentration of the reactant A changes with the time, the concentration of B and C also changes with respect to time. Okay, so your main aim is to find out the order of the reaction with respect to only reactant A. Andre rate of the reaction ಕಾನ್ಸಂಟ್ರೇಷನ್ ಆಫ್ ದಿ ರಿಯಾಕ್ಟೆಂಟ್ ಜೊತೆಗೆ ಹೇಗೆ ಚೇಂಜ್ ಆಗ್ತಾ ಉಂಟು ಅಂತ ನೀವು ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳಿ ಟ್ರೈ ಮಾಡ್ತಿದ್ದೀರಿ. ಬಟ್ ಟೈಮ್ ಪಾಸ್ ಆಗ್ತಾ ಹೋದಾಗೆ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಆಫ್ ಎ ಚೇಂಜ್ ಆಗೋದು ಮಾತ್ರವಲ್ಲದೆ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಆಫ್ ವಿ ಮತ್ತು ಸಿ ಕೂಡ ಚೇಂಜ್ ಆಗ್ತಾ ಇರ್ತದೆ. ಸೊ ಅವುಗಳ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಚೇಂಜ್ ಆಗ್ತಾ ಇರೋದ್ರಿಂದ ರೇಟ್ ಆಫ್ ದಿ ರಿಯಾಕ್ಷನ್ ಚೇಂಜಸ್ ನಾಟ್ ಓನ್ಲಿ ಬಿಕಾಸ್ ಆಫ್ ದಿ ಚೇಂಜ್ ಇನ್ ದಿ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಆಫ್ ಎ ಬಟ್ ಆಲ್ಸೋ ಬಿಕಾಸ್ ಆಫ್ ದಿ ಚೇಂಜ್ ಇನ್ ದಿ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಆಫ್ ಬಿ ಆ್ಯಂಡ್ ಸಿ. So you are not just establishing the variation of the rate with respect to the variation in the concentration of A, but also the variation in the concentration of B and C. So it is impossible to find out the order of the reaction with respect to A. ಅದೇ ರೀತಿ it is impossible to find out what is the order of the reaction with respect to B only. ಯಾಕಂದರೆ A and C will be interfering with your experiment. Similarly, it is very difficult to establish what is the order of the reaction with respect to C, because A and B now will be interfering into your experiment with C. So it is very impossible to find out the individual order of the reaction, because the other two reactants will not be sitting quiet. They will also be participating in the reaction. ಅವುಗಳ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಕೂಡ ಚೇಂಜ್ ಆಗ್ತಿರ್ತದೆ. ಅವುಗಳ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಚೇಂಜ್ ಆಗ್ತದ್ದು ಕೂಡಲೇ ಏನಾಗುತ್ತೆ, ರೇಟ್ ಕೂಡ ಚೇಂಜ್ ಆಗುತ್ತೆ. ಸೊ ಇಟ್ ಈಸ್ ವೆರಿ ವೆರಿ ಡಿಫಿಕಲ್ಟ್ ಟು find out the individual order. So what was suggested by Australs is you can find out the order of the reaction with respect to reactant A, provided if you take the reactant A in very less amount compared to B and C. That is, A should be taken in very less amount, whereas B and C should be taken in very large amount. Okay, so first we take concentration of A in very small amount and concentration of B and C in large amount. So the one with respect to which we are interested in finding out the order, that reactant should be taken in very less concentration. So first we have to find out what is the order with respect to reactant A. Then we have to take A in very small amount, whereas the other reactants should be taken in very excess amount. Okay, generally the concentration of B and C should be roughly 10 times larger than the concentration of A. So in that case we say that A is isolated from B and C, because you have taken A in very small amount whereas B and C in excess amount. We call that A, reactant A is now isolated from B and C. Now what happens, let us see. I will give one simple example to make this concept much easier to understand. Suppose I have taken A is equal to 100 molecules. Okay, I will not speak in terms of concentration, I will speak in terms of molecules. A is equal to 100 molecules and B is, okay, 10,000 molecules, roughly 100 times. Okay, similarly C is also 10,000. Suppose if you have a reaction A plus B plus C giving product, where I have mixed 100 molecules of A, 10,000 molecules of B and C each. Now, but for this reaction, for one molecule of A, you require only one molecule of B and one molecule of C. Say at the beginning, at T is equal to 0, you have 100 molecule of A, 10,000 molecule of B and 10,000 molecules of C. Say for example, I am measuring that after 10 minutes, there are 90 molecules of A left. ಅಂದ್ರೆ ಎಷ್ಟು ರಿಯಾಕ್ಟ್ ಆಗಿದೆ, 10 molecules ರಿಯಾಕ್ಟ್ ಆಗಿದೆ ಅಂತ ಇಟ್ಕೊಳ್ಳಿ. 10 molecules of A, ಎಷ್ಟು molecules of B ಜೊತೆ ರಿಯಾಕ್ಟ್ ಆಗಬೇಕು, 10 molecules of B and 10 molecules of C. So how much is remaining? 9,990. 9,990 molecules are remaining. So these are the concentration of the reactants that is remaining unreacted. So what percentage of reactant A is consumed? Initially it was 100, now only 90 is left, so 10% of A is consumed. Okay, but if I compare B and C, here 90% of A is left, but 99.9% of B and C are left. Let us proceed further. Say for example, at 50th minute, I find out that only 10 molecules of A are left. It means 90 molecules of A has reacted. So 90 molecules of A has reacted means 90 molecules of B and 90 molecules of C has reacted. So how much is remaining? 9,910. So what is the percentage change in the concentration of A? 100 was the initial concentration, now it is only 10. So 90% of A has reacted, only 10% is remaining. But what about B and C? Still 99.1% is remaining as such in the mixture. And at the end of the reaction, okay, where no more concentration of A is left, that is all 100 molecules has reacted with 100 molecules of B and 100 molecules of C. So how much molecule of B remains unreacted? 9,900. Similarly 9,900 molecules of C. So the reaction is complete, 100% complete with respect to A. But how much B and C are remaining as such? 99% of B and C are remaining as such unreacted, because there are no more A molecules for reaction. So at the given interval of time, when all 100 molecules of 100% of A has been consumed, the change in the concentration of B and C throughout the course of the reaction is only 1%. 1% of B and C has reacted and 99% is remaining unreacted. So what does it mean? Even though there is a large change in the concentration of the reactant A, the change in the concentration of B and C throughout the reaction is very very less. So the change in concentration of B and C is very very less. So we can treat the concentration of B and C almost as a constant. So those reactants which are taken in very large amount, their concentration may be considered almost as a constant throughout the reaction, whereas the concentration of the reactant which is taken in less amount remains, it is not a constant, it varies with respect to time. So if I go back to this equation, rate of the reaction dx by dt is equal to k into a to the power a into b to the power b into c to the power c. But since A is taken in less amount, B and C are taken in large amount, we have already proved that B and C are almost constant. They do not interfere now with the rate of the reaction because their concentration do not vary appreciably. So this is a constant, this is also a constant, multiplied by another constant. So you can write this equation roughly as dx by dt is equal to some constant k dash into concentration of A to the power A. Yakandre, these are all constants now. This is also a constant. So I club all these constants together and write it as k dash. So this equation clearly tells that now the rate of the reaction only depends on the concentration term of A. So now it is easy to establish what is the order of the reaction with respect to A. We can now use any one of the previous method. I can use differential method, I can use want of differential method, I can use integration method, I can use half-life method, or I can use graphical method to establish what is the order of the reaction with respect to A. Why? Because B and C are not interfering in the reaction because there is no appreciable change in their concentration. Why there is no appreciable change in their concentration? Because we have taken them in very large excess. So their concentration remains almost constant throughout the reaction. So in order to find out the order of the reaction with respect to A, we have to isolate A from reactants B and C. Then find out the order of the reaction with respect to A by any one of the 5 previous methods. So we found out what is the value of A. Then in the next step, we have to find out what is the value of order B. So which reactant should be isolated now? We have to isolate B. How will you isolate B from A and C? Take B in less amount whereas A and C in excess amount. Since A and C are taken in in excess amount, their concentration do not vary appreciably with time, and therefore during the reaction the concentration of A and C almost remains constant. So in that case, rate of the reaction only depends on the change in the concentration of reactant B. So again, by using any one of the 5 previous method, you can find out the order of the reaction with respect to B. In the third step, you find out the order of the reaction with respect to C by isolating reactant C from reactants A and B. That is, take C in less amount whereas A and B in excess amount. Again, by using any one of the 5 methods, find out the order. Add the 3 orders A plus B plus C, that would give the total order of the reaction. So remember, Austral isolation method is a new method. We use the old 5 methods for determining the order, but we make some modification, that is, we are isolating one reactant from the other reactant. Otherwise, we are following the same any one of the 5 procedure that I described earlier. So that is why we call that this as a technique rather than a method. So these are some of the important methods for determining the order of the reaction.